let's now go in more details on k-nearest neighbors. So first thing, interesting thing we have with k-nearest neighbor classification is that we have some theory around it. There are some bounds that has been proposed in the 70s that allow us to say, okay, yeah, this classifier is not just good in practice. We have also theoretical evidences that this is a good classifier. For instance, we have, let's talk first about what we call the optimal Bayesian error rate. So this optimal Bayesian error rate would be the error rate that we have if we know in advance what is the real densities of our data sets. So the point here is that we really know what is the density of what we try to model. Even if we know these densities, we will not have 100% right classification. The error rate will be non-zero, but still we consider this as the lowest error rate we can achieve given the measurements that we are making on our phenomenon. So it is, in terms of generalization, impossible to do better than that. Of course, maybe with some samples, we can have a slightly better error rate, but these are coming from artifacts of the sampling. But in terms of generalization, in terms of evaluating this with many other samples that are not seen at the training time, we should not be able to beat the optimal Bayesian error rate. And as such, there are two bounds on the KNN classification error rate. First, we know that with one neighbor, so k equal to 1 and an n tending to infinity, so a really huge data set as reference training set, the error of the nearest neighbor classifier, so the 1 and n, is less than 2 times the optimal Bayesian error rate. So we are not doing worse than 2 times the optimal Bayesian error rate with nearest neighbor classification. And with, I would say, a number of neighbors that tend toward infinity. So if we have many neighbors and a huge reference training set, we should precise here that k is still much smaller than n. So we have much less neighbors that we have samples, but still we have a lot of neighbors, super large data set. Then the error rate of our k and n will go toward, will converge, will be really close to the optimal Bayesian error rate. That means that with enough samples, with enough neighbors, we are able to estimate very well the real distribution of the data. So one way to see this is with that plot. So we can see that according to here, the x-axis is the optimal Bayesian error rate. So we have this thing here versus the error rate that we have with KNN classifier. We can see the kind of theoretical curve, which are approximated here. You can see that for k equal to 1, yeah, that value will go up and possibly go back to what we have at up to 0.5. Why with a lot of neighbors with huge data set, which is assuming with n tending toward infinity data set, the error will be the same, will be comparable between the optimal Bayesian error rate versus the KNN error rate in generalization. So if we are looking at an experiment that I've made before on using a data set of 2,000 samples, our error is about 10.7% here. So we are looking basically at the optimal Bayesian classification rate because we are computing this on real data. So in fact, these blue and red samples were coming from Gaussian distribution with different covariance matrix. So using the exact same model for densities that I use for generating these samples, I was able to classify these samples with 10.775 10% of error rate of errors. So now, if we are varying the number of observations, so we just set the model to be a nearest neighbor classifier with k equal to 1, and we are varying the number of samples used here, so with 25 at first, and then we are increasing the number of samples to 50 to 500. If we are looking at these things, so the green dash lines are the decision frontiers. We can see that around here and around there, it's fine. But we see here there's a lot of, I would say, zigzags and variations that are, I would say, not useful. These are artifacts coming from the fact that we are using relatively finite, relatively small training set. And so the decisions here are not meaningful. This is really another case of memorizing all the data and achieving some kind of decisions that are totally arbitrary around the overlapping areas between the green and red samples. However, outside this region, the decision here and there, I would say here also, this makes sense. It's really in between that it is not super reliable. These are really artifacts from KNN. With 1,000 samples, we are in similar situation, and then with if we go at 2,000, we are into something here that is still, I would say there's a small increase, slightly better, but not that much. And if we just move back, looking at the error rate, we can see here that the error is 16%, and as we go on, 12. So we are lucky here, but maybe just because that the set of 50 samples were useful here. Then 14, then 15.2, then 13.45. So these are different error rates, but still far from the 10.7 that we have when we know the real distribution. So now let's look at varying the number of neighbors. So we keep n equal to 1,000. So we are using 1,000 samples, but now we will vary the value of k, the number of neighbors that we are using for our example. So at first with one neighbor, we can see that yeah, there's a lot of variation around it. So this is what we saw before. Increasing this to 3 neighbors, okay, it seems to be slightly smoother. We have less of these variation, even though it is kind of jagged here. You know, there's kind of still a lot of variations around that region, but it seems to be less intense. And the error, in fact, is going from 15.2 up to 13.3. Going now with 11 neighbors, everything seems to be much smoother, and the error is even super low, 10.6. If you remember well, it is even lower than the optimal Bayesian rate, but this is not significant here. This is just, I would say, an artifact that we are lucky on our 1,000, our sample set that we use as testing. So this is not meaningful. I would say don't bother on this. But here we are going into something that is better than k equal to 1 and k equal to 3. And if we go even with more neighbors, with 23 neighbors, the estimation is kind of smoother. Of course, it is kind of off in that region, but not that much. It seems to be quite well fit on the real distribution in the other region on the right. So this is fine. This is in fact quite good. And it shows, I would say, the capacity of nearest neighbor classification to estimate the real distribution with enough samples and enough neighbors. And then the error is even lower than before, but again, these are, I would say, sampling artifacts, the fact that we are lucky in our test set to have enough data to classify them well. Because when we are increasing this to 57 neighbors, the error is increasing. So but these are only variations. And we see that things are kind of smooth here. You know, it's really smooth around that decision frontier. So everything is kind of fine, except maybe on the left, but that's possibly because we have only few samples in these regions. So these regions doesn't have much samples, so the estimate is kind of slightly off, but it's not meaningful. So this was the effect of N and K, the data set size, and the number of neighbors. So now if we are looking at the distances used, so the distance measurement, so far we were using the Euclidean distance, which is a good choice, but this is not the only choice. In fact, the distance here is giving us the measurements for determining the neighbors. So it is a way to evaluate the relationship between the data. So in fact, we are looking to get some metric, and there is some kind of formal mathematical definition of a metric. So we are working on the X by X space, and this is giving us a real value as the distance measure. So at first, we want to get a distance measure that is non-negative. We want the distance to be always either equal to 0 or positive. So this is important because a negative distance doesn't really make sense, and it breaks many things in terms of what we are doing with it. We want it to be reflexive. So if we've got a distance of 0, we want it to be for equal samples. So X and Y here are the same. We don't want a distance of 0 for 2 points that are different. We want it to be symmetric. So the distance from X to Y is the same as the distance from Y to X. If it is not symmetric, it breaks some notions that we have about metric, a mathematical definition of metric. And the last thing is that we are looking at what we call the inequality of the triangle. So we assume that the distance between X and Z is less or equal to the distance between X and Y and Z. Look at it. For example, we have a triangle. We have X here, we have Y here, we have Z here. So the distance between X and Y is something like this. And this distance should be less than the sum from X to Y and then Y to X. The only case where these are equal would be, for example, we have X, we have Z, we have a distance, and Y is in fact on that trajectory. So basically, the distance from X to Z is equal to X to Y and Y to Z. Otherwise, if Y is not there, is there, for example, then that distance should be higher than the distance, direct distance from X to Z. So with Euclidean distance, this makes sense, but we can have, there are several other distance measures that can be used, which will respect these, this definition of a metric. So we know the Euclidean distance, but there are also what we call the Minkowski distance, which is a generalization of the Euclidean distance. We have also what we call the Tanimoto distance. This is quite different. This is a distance between sets. So instead of working in a vector of d dimensions, we are working with sets, and we are able to measure some kind of distance according to this distance. We have the tangent distance, which is kind of distance between 2 points, but we have a reference, a third reference point usable for that. Going back to the Minkowski distance, which, as I said, is a generalization of the Euclidean distance. The general formulation is this. So we have a p parameter, and that p parameter is configuring somehow that distance measure. So it controls the emphasis on the dimensions where the magnitude is the greatest. So when we say, okay, we have dimension with big difference, so all important is that big difference in the overall distance measure. So we have one distance measure that is called the Manhattan distance. So p equal to 1. We put an equal weight on all dimensions. So we say Manhattan distance is equivalent to summing all the absolute differences between the for variable I, the xi versus the yi over all dimensions. We call this Manhattan distance. It was also called city block and others because it looks like how do we compute the distance on the Manhattan Island in New York City. For example, we have in fact avenues like that. We have streets like that. And we know that if we want to go from that place to that place, I would say direct connections like this, which is corresponding to the Euclidean distance, is not possible because we are not able to get through buildings. So we need to, in fact, take this path and then take that path. This is not the only distance. We can do different paths. This one is also valid. This one is also valid. But these are all equivalents, and we just need to, in fact, compute the number of steps in X and the number of steps in Y to achieve the destination. So this is putting an equal weight on all dimensions, and this is corresponding to the Minkowski with P equal to 1. We also have another one, which is called the D infinity. So this is using only the dimensions where the difference is the maximum. So we don't care about other dimensions in the sense that we are looking at the difference or the distance for each dimension individually, and we keep the maximum one. So if we go back to our example with Manhattan, it will basically say that we have that here for X, that here for Y. And so the X here is much higher than that one. So in such case, we have only this one that is used as the distance, and we just don't care about the other one. So this is really put it all emphasis on the biggest difference. And as for Euclidean distance is Minkowski with P equal to 2. So it's making a trade-off between these two extremes. So we are putting more emphasis on the biggest differences. For example, if we have a difference between, so we have still our example, but here let's say that we have equivalent of this, which is 2, let's call it 2D, and this is 1D. So we have twice the distance on X versus the distance on Y. So in such case, what we know with Euclidean distance is that we will put 4 times more emphasis on these difference on X, on X1 versus the difference on X2. So it's a kind of trade-off between these two. We put more emphasis on bigger distances, but we are not ignoring the smallest ones. And Euclidean distance is like really the direct connections between 2 points in the kind of what we represent ourselves as a 2D space. So this is kind of really intuitive way to see a distance. So to illustrate the Minkowski distance, we have these different examples. I would say at first, all these top values here are not that meaningful. I mean, these way to compute distance are not very intuitive, so I don't see why they will be useful, but they are here for illustrating the approach. This first one here is the Manhattan distance. So basically it says that, you know, on this diamond here, everywhere we will be on the blue line for the diamond will be at equal distance from the origin. So we are here or there or there. In all cases, the distance to the origin is the same, is equal to 1, for example, here. As for the other here, we have this one. So P equal to 2. This is the one with the Euclidean distance. And in fact, according to the Euclidean distance, we are at the same distance from the origin on a circle. So being here or there on that circle, this blue circle correspond to equal Euclidean distance from the origin here. With bigger P, we can see that the circle is coming closer and closer to a square. And then we have the case of P equal to infinity that correspond to the infinity distance. So this one basically said that whatever we are on the square, we are at the same distance. So in fact, here we can see that all this square here is at the distance of 1 according to the infinity metric. One thing we should keep in mind is that the distance measurement is sensitive to the data scale of all the dimensions. So if we don't have scales that are, I would say, equivalent, comparable, then our distance measurement may not be as good as it should be. So value in a dimension where the scale is large relative to the other dimensions will absorb the value of the other dimensions. So basically, this is the idea that when we have a big difference, this will count for much of the distance versus the other dimensions. An extreme case is with the infinity, where we are only using the value for the highest difference. But if we know that our measures are not with the same scale or are not with the same units, if we are measuring things and the scale is in 10 power of 3 versus another measurement where the scale is around plus or minus 1 times 10 power minus 4, this is not at all comparable, and the first dimensions will absorb everything, and we will ignore any kind of differences on the second variable. So this is important, and so we often need to renormalize everything to be comparable, or at least get our values on the scales that are comparable. So standardization is required if the scales are different. And we can use, for example, the physical units. If we are working with measurements that are meters, millimeters, kilometers, it's easy to just get everything back on the same scale. And as such, using the physical units to make things comparable. But this is not always the case, and sometimes we may need simply to look at what are the minimum, maximum values possible in each dimension, and we scale them to be like, for example, in the -1 + 1 range. So getting everything renormalized between -1 and +1 allow us to make things that are comparable. So this is a way to proceed, even though if the data is not uniformly distributed between the max and min values, this is maybe not the best one. So we may want to use things like white-lining transformation that we will see toward the end of the semester, which is basically trying to get our data normalized to have a multivariate Gaussian distribution with zero mean, with in fact, an identity covariance matrix. So no covariance, and the variance on each unit, on each dimension is unit. One interesting thing with KNN classification is that no training is required. What we need to do for training is to memorize, to store the data set X that we have at N. So with such setting, leave one out classification is in fact possible. So we can evaluate performance in a leave one out way because no training is required. So this is nice for that. This is really nice. And as such, we can evaluate performance with even small sample sets. And leave one out, if you remember well, it corresponds to k-folds cross-validation using a k = n. So that means that if we have n samples, we will make n trainings and evaluate training on n-1 samples, test on the remaining sample. With KNN, given that there is no training, is basically to say, okay, let's take one sample from the training set and evaluate its k-nearest neighbors over all the remaining samples and classify it according to KNN rule. And repeat this for all samples. So the cost of doing this, we can implement leave one out very efficiently for KNN classification by not having to do any kind of training. So this is done by having an algorithm that goes from, for each data in the training set, or in our data set, we compute the k-nearest neighbors according to all the training set except the sample xt that we care. We determine the most common label, so we just get all the k-nearest neighbors samples to vote according to their labels and assign the sample to the class that has the most samples here. And from these assignments, we are evaluating the error rate as the overall error rate for classifying all the samples according to the KNN from the data set of all the training set except the data itself.